Okay, we're doing the second part of this problem of uniform circular motion on an incline. And the second part of the question is, were there no friction between the car's tires and the road? What centripetal force could be provided just by the banking of the road? Taking the liberty of drawing a diagram, or adding to our free body diagram, and let me explain it to you. We have weight and we have the normal force, and I've then figured out what is the angle of the normal force with respect to the positive x-axis going counterclockwise. And we found that because we know that this incline is at 27 degrees, we know that this angle is 27. And if this one is 27, then this one is. And this is 90, so 27 plus 90 is 117. Okay, we're looking for what force could be provided by the banking of the road. Well, the centripetal force is the net force of a system, and it is a center-seeking force. And so we're just looking really for the net force of this diagram. Now, we need to look at it in both the x and the y dimension. And what you'll see pretty clearly is, I'm just going to write F net for the equation because we're really just adding the forces. But you'll see pretty clearly that if you see this here, the forces the force that provides the centripetal force has to be the normal force here, because it is the only force that has a component in the x direction, and that is the direction of the uniform circular motion. So it's the direction of the center-seeking force, or the force that is needed in order to have this object move with uniform circular motion. In the y dimension, the forces are balanced. There is no change in motion of the car in the y dimension. And I've drawn like a diagram here where you show this circular motion, and you almost have to imagine that this motion is taking place on an xz plane, and that the y axis goes right through and is perpendicular to that plane. And the object is not moving up or down the x-axis as it moves around this xz plane. So I'm going to sum the forces in the x direction, and that's my net force. Now, the sum of the forces in the x direction, I think it's pretty obvious that it's just the x component of the normal force. Okay? And I can write that out. I know that the x component of the normal force is just the normal force times the cosine of the angle of the normal force, which is 117. Unfortunately, I don't know what the normal force is, but we can figure that out. And we do that by summing the forces in the y direction. And so in the y direction, we have the normal force in the y direction plus the weight in the y direction, and those have to add up to 0. Those are balanced. And so we can then define these in terms of their angles. So Fny is really Fn times the sine, 117, and the weight in the y direction is the weight times the sine of 270 degrees, and that adds up to 0. So if we take the sine of 117, we get 0.8910 Fn, and the sine of 270 is -1, so this is minus W equals 0. So if we move W to the other side and divide both sides by 0.891, we get Fn is equal to W divided by 0.8910. And that is equal to 1.122 times the weight, right? Weight. And that is equal to 1.122 times the mass, which is 2.99999 times 10 to the 3 kilograms times 9.8 meters per second squared. And that is going to be equal to that's going to be equal to 32,987 newtons. That's Fn. We want to know what is Fnx, because that is the component of the normal force in the x direction, which is the force provided by the banking of the curve. It's the part of the normal force that's in the x direction. So Fnx is equal to 32987 times the cosine of 117 degrees, and that is going to be negative 14,970, let's make it 6 newtons. Okay, this is the magnitude and direction. We are only looking for the magnitude. So Fnx is equal to 14,976 newtons. Is equal to 1.122 1.122 W. Okay. So we could figure out what Fn is. If we can figure out what Fn is, we can plug that into this value here, and we can determine what Fnx is, which is what we're looking for. W is equal to the mass times the acceleration due to gravity. So this is going to be 2.99999 kilograms times 10 to the 3 kilograms times 9.8 meters per second squared. Okay. And